Hey everybody, welcome to the periodic table. A brief history of the table. In 1829, J.W. Dobereiner attempted to organize the semblance of a periodic table by publishing a system where he grouped the elements in groups of 3, hoping that they would make sense together. And what he found was that every 2 elements, he found that the middle one always had a value within the other 2. Just a little attempt to start grouping the elements together in a way that made sense. Dmitry Mendeleev is the one that really did the bulk of the work. The Russian, there's a great story that he rode the train to and from his home, and he spent a lot of time just looking at the ice, and he would make flashcards. He would make these paper cards with the names of the elements and group them together like a deck of cards to see if he could group them in a way that made sense. And so he organized the elements by repeating properties based on mass, which we know today is wrong. He's the one that, like I said, did the bulk of the work, and he left spaces for elements that he knew weren't discovered yet but that were coming. It was Henry Moseley in 1913 that actually figured out the key to the periodic table, and he discovered that it was supposed to be organized by atomic number and not atomic mass. There's a law called the periodic law that says that when the elements are arranged properly in order of increasing atomic number, that's when they start to show their properties and their patterns. So only when the elements are arranged by atomic number, that's when the patterns really start to show. If you arrange them alphabetically, the patterns will not show. If you arrange them by mass, the patterns won't show. They have to be arranged by atomic number for the patterns to actually start showing. Today, the periodic table is arranged by atomic number, and that is a very important test concept. As you know, the periodic table displays the symbols and the names on these squares, along with information about the structure, for example, the atomic mass, the atomic number, and some of the periodic tables are color-coded. The black ones are solids, the red are gases, and the liquids are blue. Every periodic table in the world has the same information. On the top here, you have the atomic number here, and on the bottom, as you remember from chapter 4, you have the atomic mass, which is the average of all the isotopes, and then somewhere in the square you have the element name, the element symbol, and some tables even give you the configuration in each level. So for example, the 281 means that the configuration for sodium is 1s2, 2s2, 2p6, 3s1, and this 6 and the 2 make this 8 that you see here. Pretty clever. From our notes, you remember that there are certain groups of the periodic table that you have to memorize the names for. Group 1 are the alkaline earth. The group 1 are the alkali metals, and hydrogen is not one of those. Group 2 are the alkaline earth. These in the middle in the D block, these are the transition metals. Then you have the halogens and the noble gases. Down here we have the lanthanides and the actinides. They constitute the F block, and those are also called the inner transition metals. Going down on the periodic table, going down is a group or a family, and going across is a period, a row, or a series. Again, here are the special names that we talked about. It's helpful to know that periods go across the periodic table. There are 7 periods corresponding to the 7 rows on the table. Row 1 fills up to 1s2, as we know. Row 2 is 2s2 to 2p6. Row 3 is 3s2, 3p6. Row 4 is 4s2, 3d10 up to 4p6. Row 5 is 5s2, 4d10 up to 5p6. Row 6 has 6s2, and then it goes to 4f14, then 5d10, then 6p6, and row 7 is the rest of the elements: 7s2, 6f14, 5f14, 6d10, and the rest of the elements up to 7p6. It's important to note that the majority of the periodic table are solid metals. All the metals are solids except for mercury, number 80. The metals are underneath a zigzag line, and they comprise about 80% of the table. Metals have specific characteristics. They're good conductors of heat and electricity. All are solid, like I said, except for mercury, number 80. They're lustrous. That means that they're shiny and reflect light. They're ductile, which means they can be drawn into wires, and they're malleable, which means that they can be hammered into thin sheets and foils like aluminum foil and gold foil, for example. Here are some sample metals that we all know and love: aluminum, gold, silver on the upper right hand corner, then potassium on the lower left, and calcium. Mercury is a metal, and it's the only liquid metal that we know, and it's toxic, so be careful. And bromine is the only other liquid at room temperature on the periodic table, and it's the only liquid non-metal. As we know, it's valence electrons that are responsible for an element's behavior. Remember, the protons are identity, but the electrons are behavior. Elements in the same group have the same valence number. That's a really important idea on this exam. The table is also named by blocks, which we already know. The S block right here, the D block, the P block, and the F block. As we were mentioning before, the groups have names. Group 1A are the alkali metals. Group 2A are the alkaline earth metals. Group 7A are the halogens. It's important to note that the alkali metals do not include hydrogen. If you look at the group going down, 1s1, 2s1, they all end in s1. This is called the s1 line. S1 over here. Two S1, 3s1, 4s1, 5s1, and even though there's these D's in between, it ends in 6s1 and 7s1. That means that they're all going to behave in a similar way. All the alkali metals end in S1, and all the alkaline earth metals end in S2. Here are the noble gases and the halogens. Elements can be sorted into 4 different groups based on their configurations. So the periodic table is basically split up into 4 areas. The noble gases, the representative elements, which are all the S's and the P's up to the noble gases, the transition metals in group in the D block, and then the inner transition metals that are the actinides and the lanthanides. The noble gases are very important. They're in group 8A or group 18. If you look at the modern way of labeling the table, they used to be called the inert gases, inert meaning unreactive, because they rarely take part in a reaction. They're very, very stable. They have a complete outer level filled in, so they don't want to gain any electrons. They don't want to lose any electrons. Noble gases have an electron configuration that has the S and P levels completely full. S and P. Look at the noble gases. They all have 8 valence electrons, 6 plus 2. 6 plus 2, remember why we're not including the Ds, because they're a level lower than a level 4. 6 and 2 on a level 5, not including 4D. Again, right here, 2 and 6 make 8, not including the 5Ds and the 4F14s, which are a lower level and not considered valence. So all of the noble gases have 8 valence electrons, except for helium, which is happy with 2 valence electrons. The representative elements are considered groups 1A through 7A. Notice that this does not include the noble gases. They're called the representative elements because they display a wide range of properties, and so therefore are good representative of all the different types, meaning that some are metals, some are not a metal, some are the metalloid, some are solid, others are gases, others are liquids. What characterizes them is that their outer S&P electron configurations are not filled, so they are looking for stability by either gaining or losing electrons. So here's the representative elements. It's group 1A right here, group 2A, skip transition. Then it's group 3A, 4A, 5A, 6A through 7A, not including the noble gases, which are their own area on the table, and not including the transition metals, which are their own area on the table as well. The transition metals are considered to be in the D block. They are elements that have electrons that fill up the D rows, the D orbitals. And in the old way of labeling the table, they are the B elements. Again, here is transition area right here, very nicely highlighted on this table. Remember the exceptions, chromium and copper. Chromium used to be an S2 and a D9, or excuse me, an S2 and a D4, and then it changes over into a S1 D5, and copper used to be an S2 D9, and it changes into an S1 D10 for more stability. So again, S2 D4 changes into S1 D5, and S2 D9 for copper changes into S1 D10. Remember that the d orbitals are one level behind, so that if you're in period 4, you're really a 3D. F's are 2 levels behind. This is a blank periodic table for you to practice. Do you remember what this group was? If you said alkali metals, you're right. What about group 2? That's alkaline earth metals. This area, the transition area over here, the halogens, this last group, the noble gases, and down here are the inner transition metals, and also known as the actinides and the lanthanides. Okay, periodic trends. This is where things get a little bit more difficult and abstract, so let's go through this. All periodic table trends are influenced by 3 things. The level that those last electrons are away from the nucleus, also known as distance from the nucleus. Number 2, the nuclear charge. And number 3, the shielding effect, also called the blocking effect. The first periodic trend is radius or size. It's the distance from the center of the nucleus to the outermost electron. And remember, it's really hard to take the distance from the nucleus to an outer edge when it's so fuzzy like an electron cloud. So they take 2 homonuclear atoms, 2 atoms that are the same, and measure the distance from nucleus to nucleus and take half the distance, which is very clever to do. The trend is that the size increases as you go down, and it decreases as you go across. Now, there's reasons for this which we have to know, so let's go through those. This is the definition of the radius, again from nucleus to nucleus, and then half the distance. So as you go down a group, you need to imagine these atoms getting larger. Let's go back here for a second. As you go down a group, the nuclear charge is increasing, but you have the benefit of having a level change, which means that these last electrons are further away from the nucleus, which makes them more loose, and also every time you gain another level, you gain another shield. As you go across a group, you need to imagine the atoms getting smaller. That's because their nuclear charge is increasing, but they don't get the benefit of a level change. And so since they don't get the benefit of a level change, you also don't get the benefit of any more shielding. These are, this is the trend for radius shown by period. Let's talk about ions. An ion is a neutral atom that has either lost or gained an electron. Remember, you can have either a positive ion, a cation, or a negative ion, which is an anion. Let's talk a little bit about metals again. Metals tend to lose electrons. They're on the left-hand side of the table. Non-metals tend to gain electrons. They're on the right-hand side of the table. So they're closer to gaining electrons and being closer to the next noble gas by gaining electrons rather than losing electrons. Just something a little cute and fun for you to look at. Perhaps one of you gentlemen would mind telling me just what it is outside that you find so attractive, and it's the cations being attracted to the anions. I thought that was pretty good. Ionization energy, that is another trend. That is the energy required to remove an electron, the outer electron, from a gaseous atom, because in a gaseous atom, the atom is in the highest vibrational state. It's measured in joules per atom or kilojoules per mole. The mole is something that we're going to see in a couple months. Removing one electron makes a positive ion. So removing the lost electron from an atom is called the first ionization energy. Removing the second is called the second ionization energy. Removing the third is called the third ionization energy, etc. You can have as many ionization energies as you have electrons in an atom. And there is a definite trend. The trend is that ionization increases as you go left to right on the periodic table, and it decreases as you go top to bottom on the periodic table. Let's take a further look at this. As we said, the second ionization energy is the energy required to remove the second electron, and the second ionization energy is always greater than the first, and the third is always greater than the second, and the fourth is always greater than the third, etc. There's always an area where the ionization energy spikes or increases the most, and that is whenever you try to take electrons away from a noble gas core. The factors that determine ionization energy are very similar to what the factors that determine why the radius gets larger as you go down and smaller as you go across. As the atom gets smaller, as the nuclear charge gets bigger, the ionization also increases. So in other words, as the atoms get smaller going across the periodic table, these lost electrons hold on tighter because they're closer to the nucleus. And as the atoms get larger as you move down a group, these last electrons are held more loosely since they're further away from the nucleus, and they're better shielded by the shielding effect, so the ionization energy actually decreases. So as the radius increases, the ionization actually decreases, and as the radius decreases, the ionization actually increases. Shielding is the protection that a last electron gets from the levels that are below it. That is called the shielding effect. Electrons in the same period have the same shielding. They don't get the benefit of any additional shielding. As we said, as you go down a group, the ionization energy decreases because these electrons are getting further and further away from the nucleus. Plus, there's more shielding. As we were discussing for the radius, all the atoms in the same period have the same shielding because they're not getting any new levels. They're in the same period on the periodic table. Okay, these last slides, you don't have to worry about these two slides, or this one, or this one. This is getting very specific. This is showing the trend in the ionization energy going across a period. As we were discussing in class, it is very, very difficult to remove an electron when an energy level is full. So when you try to take an electron away from a noble gas core, the atom is going to be very, very resistant to doing that, and the energy will spike. The energy There's also a trend in ions. When you make an ion, let's go down group 1. So now instead of just a normal lithium atom and a normal sodium, a neutral sodium, and a neutral potassium, and a neutral rubidium, and a neutral cesium, we have their ions. The ions show the exact same trend as the neutral atoms. Isoelectronic atoms or isoelectronic ions are ions that have the same number of electrons. Iso means the same. Electronic refers to number of electrons. So isoelectronic means same number of electrons. All these ions right here have the same number of electrons. Al3 plus is 13 minus 3 or 10. Mg2 plus is 12 minus 2 or 10. Sodium 1 plus is 11 minus 1 or 10. Neon is a neutral atom that has 10 exactly. F minus is 9 plus 1 equals 10. O2 negative is 8 plus 2 equals 10. And N3 negative is 7 plus 3 equals 10. So we can see that they all have the same number of electrons, but yet they're all still the different ions because they have a different amount of protons in the nucleus, and therefore all of these have different sizes. So they have the same configuration, which means that they're going to behave in a similar way, but they're all going to have different sizes. So let's talk about those sizes. Even though all of these have 10 electrons, the biggest size is going to belong to N3 negative because you have 7 protons still in the nucleus, but you have 10 electrons, so this atom is going to puff out, followed by O2 negative, 8 versus 10 electrons, 9 versus 10. Neon is neutral at 10. Sodium is going to shrink because it has 11 electron versus 10, so it's going to pull inward. Magnesium is 12 versus 10, and aluminum is 13 versus 10, and that's going to be the smallest. So aluminum is the smallest, and N3 negative is the largest. The rule is this: positive ions always shrink, and a negative ion always gets larger than the neutral version of the atom. So For example, between N and N3 minus, N3 minus is larger. Between aluminum and aluminum 3 plus, aluminum is larger. There is another pattern called electronegativity, and that was discovered by Linus Pauling. He created the famous Pauling table. And electronegativity is defined as the ability to attract electrons as opposed to ionization, which is to remove. So electronegativity is about attracting electrons in a chemical bond. So we have to be talking about two atoms that are bonded to each other. It's a unitless number. The table goes from up to 4. The highest number belongs to fluorine, and the lowest number belongs to francium with a negativity value of about 0.7. The pattern 4, it increases going across and it decreases going down, just like the ionization. I hope this better helps you understand the patterns on the periodic table. Any questions, please email me. Is that